if you look at the chart on the right, I've heard people say before that, we could have, and I just locked my screen. We could have built an Exascale machine 5 years ago or 10 years ago, and that's true. But you couldn't power it. So if we tried to build an Exascale machine with Jaguar, it would have taken 3 gigawatts a year to power it, which is equivalent to about $3 billion. And you can see with Titan, there was an order of magnitude improvement in the efficiency, but it still would have cost $330 million to pay for that 330 megawatts of power. And then, Summit was better by a factor of 5. It's still not affordable. And with Frontier, we actually exceed the target. The target was 20 megawatts, or you could look at it as 50 gigaflops per watt. And at 1.1 exaflops at a 21 megawatt power, we were just above that line. So we exceeded that goal. And that's due, to the inclusion, the GPUs helped a huge amount, as you can see here, but it was also the Star Forward programs and, use of direct water cooling. We started that with Summit. We liquid cooled the CPUs and the GPUs, but we still used air cooling for the NICs and the DIMMs and the power supplies and the SSDs. But with Frontier, that is all liquid cooled. And I'm trying, here we go. Got to get rid of that box, thanks. All right. Oh, one more note on power. This blows my mind every time I think about it. If you take one cabinet of Frontier, it has a 10% higher HPL run than all of Titan. That's only using 309 kilowatts compared to Titan did it with 7 megawatts. And that cabinet, it's 2.5 meters squared versus over 400 meters squared for Titan. So that just blows my mind every time I think about that. That is a huge improvement in power efficiency, but also density, a very capable system. This is looking at the last 3 systems. This chart has been shown before. I'm not going to spend a lot of time on it. The only thing I'd really updated here is before we would say 1.5 plus. And the way that Frontier is currently configured, it's a 1.7 exaflop system. You'll see in some of Oak Ridge and HPE and AMD's marketing materials referenced as a 2 exaflop system. It is theoretically possible to configure the system as a 2 exaflop system, but it's not configured that way at the moment. And that's one of the things we're evaluating to see if that's something that we could actually do in a production environment. I think the only other things that we've updated on the slide is, adding the names to the CPU and GPU. So Trento is basically a Milan with a custom IO die. I'll talk about that a little bit coming up, and then adding the MI250X name to the GPU. Looking a little bit more at the interconnects, going back to Jaguar, it was a C-star interconnect from Cray. Node injection was 8 gigabytes a second. It used the Portals 3 interface and a 3D torus topology. We did an in-place upgrade going to Titan. So we used the same cabinets and the same cables in the back, but we replaced the motherboards, which included changing out the NICs and the routers that were part of the C-star. It replaced it with the Cray Gemini interconnect. Node injection, this is kind of a weird one. Titan doesn't exist, so I can't actually go on and log on and see what it is. In my notes, I had it at 6.4 gigabytes, but I've seen presentations online that claim this was anywhere from 5.5 gigabytes up to 10 gigabytes a second. And then the interface was a Cray designed one called Eugenie. It was the user space general network interface, but it used the exact same 3D torus. So we were lucky in that the cables could be reused. When they spec'd Jaguar, they bought really nice cables, and those cables were sufficient to be used at a higher bandwidth for Gemini. For Summit, we switched to Mellanox EDR InfiniBand. This was ConnectX 5 HCAs. It was 2 100 gigabit port HCAs. ConnectX 5, I said, there were 12.5 gigabytes a second. The interface is verbs, and the topology was a CLO network or a non-blocking fat tree as most people call it. But when I worked at Maricom, Chuck sites beat into our heads. If it's non-blocking, it's a CLO topology. With Frontier, we've gone to HPE Slingshot. Slingshot is a superset of Ethernet, and Keith Underwood, again, will be talking about this at his 2:30, I think it's 2:30 talk. There's 4 injection ports, each 200 gigabit or 25 gigabytes a second. The interface is libfabric, or some people call it OFI, and the topology is a 3-hop Dragonfly. And Dragonfly was really designed to emphasize the trying to keep the cost of the network down. So they do that. It has fewer cables. It's a direct topology versus an indirect. And they try to keep as many cables short so they can be electric, and only use the optical cables when they have to. And you can kind of see the difference. One of the fun metrics that we like to share is if you laid all the cables end to end, how far they reach. And I've converted these to metric for our friends over in Europe. So Summit has over 300 kilometers worth of cables, and Slingshot and Frontier only has 150. So from Hamburg, I think you could probably reach those all the way over to Hanover. But I'll talk a little bit more about differences later. All right, this has been shown before. Again, I just updated the exaflop number. There's 74 compute racks. The system is provisioned. It can theoretically generate 29 megawatts of power. So far, I've not seen it go over 25. Initially, we put in enough power in the room to go to 40, but the system is designed to theoretically only go to 29. The memory there is base 10. But if you did it in base 2, it's 8 PB, and that's 4 PB each of HBM and DDR4. Lots of storage. The Olympus rack is I'm assuming Cray has, or HPE has one over in their booth. You should take a look if you haven't seen one up close. It is a very, very dense design, also very, very heavy. So in the US, it's 8,000 pounds. And that's roughly the weight, almost exactly the weight of 2 F-150 pickup trucks, which is the best-selling vehicle in the US, but those probably don't sell very well in Europe, so I looked it up. That'd be equivalent to about 1.5 Mercedes G550 trucks or 2 Land Rover Defenders in much less space. And then the motherboard, we'll talk about that in a couple more slides. So let's look at a block diagram of the Bard Peak node. Bard Peak is the code name for the blade used in Frontier as well as Lumi and Ad Astra. It has a single Trento CPU and 4 MI250X GPUs. Trento is a Milan with a custom IO die. So if you go to the AMD materials for EPYC, you'll see they've gone to this chiplet design. You have 8 CCDs, and those are core compute dies surrounding the center IO die. The IO die has the memory controllers, the PCI lanes, and there's a network on that. The difference between Trento and Milan is that all the PCI links, the 128 links that are on a Milan can also speak XGMI on Trento. So that's really the only difference there. And then if you look at the MI256 on the right, you'll see there's actually 2 graphics compute dies inside of each OAM, which is an open compute accelerator module. And those are connected by XGMI 3. So that's the higher speed. Those are 50 gigabyte links. So if you look inside that package, that upper one on the left, that has the dark green and the light green, and hopefully the colors are showing through there. There's 4 parallel links, so each one of those is 50 gigabytes, so theoretically 200 gigabytes. And then if you look at the OAM below that with the red, those are connected by 2 links, so that's theoretically 100 gigabytes. And then the east-west links are 50 gigabytes each, and those you cannot stripe over because they originate from 2 different GCDs and land at 2 different GCDs. And then the gray line and the brown line, the colors are just to help you see the difference, but they are the same. They're the 50 gigabyte links. and they're diagonal links. So if you look at the brown one, it goes from the upper green in the upper left down to the light orange in the lower right. And then the gray link goes from the dark red in the lower left to the light yellow in the upper right. One interesting thing to note here, each GCD is connected to 3 others. So it either has, all of them have at least one vertical link and one horizontal link. And then they either have a second vertical link or they have a diagonal link between them. And then the purple little connections are PCI Gen 4 extended speed mode. So this runs also at 50 gigabytes a second, but it's PCI Gen 4. It's just overclocked. And that connects to the Cassini NICs. And then the Cassini itself is 25 gigabytes. And I prefer gigabytes. I don't use the gigabits because the first thing everybody does is try to convert that back to gigabytes. So I save them in the middle the step of doing that. The reason why it's twice as fast as the Cassini is the Cassini, you know, Chris or Keith will talk about this later. One of the things they did was try to improve the message rate by altering the Ethernet standard. But at small packets, you have lots of overhead. So the idea here is that you over provision the bandwidth to the NIC so that you can afford to send more packets down to the NIC, and then the NIC can then efficiently put those out on the wire to improve that message rate. What I don't show on this diagram are the links from the CPU out to the GCDs, but I've color coded them. And so in effect, what you have is a link from each CCD out to one of the GCDs. So it's a one-to-one mapping. But those links don't come directly from the CCD. They come off the IO die, but they're very close to the CCDs where they originate. And something else to be aware of, if you're using a machine that is based on this node board, or anything right now that uses an EPIC processor, is you can configure the NUMA on the Milan or the Trento or even the Rome CPUs to be either a single NUMA, they call that NPS or NUMAs per socket 1. Some can do NPS 2 and some can do NPS 4. So Frontier is configured with NPS 4. And so if you looked at the Trento, those 2 red ones, the dark red and the light red, those would be in a NUMA quadrant. And then each corner is a NUMA quadrant. There's 2 memory controllers that are associated with each one. If you run a single application across the CPU, you probably want to run an NPS 1, something like a web server. But HPC apps, because we use MPI and we tend to partition the application itself, it makes more sense to use NPS 4. There is a cost for using NPS 1. If you run stream, you'll only see about 150 gigabytes a second out of the memory when you're in NPS 1 mode. If you're in NPS 4, you'll get about 170 gigabytes out of the theoretical 205 gigabytes a second. So that's if all 4 are accessing memory at the same time. And but that's how we expect most of our users to run. Now, if you are in your application, you want to have a shared table, right? Because you don't want to have 4 copies of it, but you want everybody to access it. What you really want to do with that table when you allocate it is use HWLock to interleave that one buffer across all 4 so that they can all equally share it. Otherwise, one will get great access and the other 3 will get really crappy access to that data. And speaking of data movement, in the all those XGMI3 links on the right, there's actually 2 ways with AMD to move that data. So if you're implementing an MPI and you're trying to figure out how you want to do data movement when the user is calling an MPI send or receive, or doing RMA, you can launch what they call a BLIT kernel, B-L-I-T kernel, and that basically all it does is uses 1 or more compute units or CUs, equivalent of an NVIDIA SM, to just basically read from the source and write to the destination. And if you do that, it can use all of those links in parallel. It'll, if you're doing from the dark green down to the light green here, it will stripe over all 4 of those, and you'll get probably on the order of about 170 gigabytes out of that theoretical 200 gigabytes. And likewise, if you're going this north-south route between the OEMs, you'll get a little better than 70 or 80 gigabytes a second out of the theoretical 100. Anything going east-west, that crosses the center line, you only get 50. It doesn't matter if it's a diagonal link or a horizontal link. The problem with the blit kernel is a CU has to do the work. So if the user is using all the CUs because they're trying to squeeze every little bit of performance out of the blade, your data movement is going to have to queue and wait until a CU becomes available. So even though you've launched an asynchronous kernel, it may not execute. It will serialize behind work on the CUs. They have an alternate method using SDMA engines that will actually truly work asynchronously. You can fire and forget. But the downside is it cannot take advantage of these parallel links. So it doesn't matter if you're going between these two GCDs or these two GCDs, it will only use one of those 50 gig links at a time. So your performance will be capped at 50 gigabytes. So that's the trade-off. It's higher bandwidth, but potential queuing, or lower bandwidth that happen in parallel. The other interesting thing about the design here for MPI implementers is that each GCD, I think I mentioned this before, is connected to three others. You have that, like I said, one or two vertical links and then one horizontal and potentially one diagonal link. This allows you to do some interesting optimizations for collectives because you can be doing data movement in three directions at once. And there's plenty of memory bandwidth on those GPUs. So each GCD has 4 HBM stacks and is capable of 1.6 terabytes a second. And so with, within the OEM package, it's 3.2 terabytes, but there's plenty of memory bandwidth to saturate those links. All right, I think that's it. Talked before about how dense these cabinets are. This is a single blade. This is 2 nodes. And so what you see up here is the GPUs on top. This is kind of rotated 90 degrees from what we just looked at. The CPU is here in the center. The DIMMs are above and below it. There's 2 NICs here. There's 2 NICs here. What's not shown is there's a card here called a bunny card that holds two SSDs that go on top of the CPU cold plate. And then the water connection is on the front, and then on the back of the blade, there's the 4 blind mate connectors for the networking. Those are dual port connectors, and then there's a power connector in the back that engage when you insert it into the chassis. And then down here, just talking about everything being water cooled. This is just a cooling loop showing you all the many different paths the water can take, and trust me, there's many, many, many paths. Okay. So once you have the blade, you have a chassis. The chassis, there's 2 chassis here on the left. You have 8 blades or 16 nodes slot into this chassis, and then rectifiers in the center. And this is the second chassis doing the same thing here. Flip it around. The switch modules go in horizontally, and so that a single switch module, when it goes in, will connect to all 8 of those blades that are vertically inserted on the other side. The technicians sometimes say they have to go out and do a Shasta hug. Shasta is the name that Cray had for the cabinet design. Sometimes when you push one in from the front, it disengages the one a little bit in the back. So you kind of go out there and give it a big old hug and push everything together to get them to mate up nicely. So once you have the chassis loaded, you have 8 chassis per cabinet. That's 64 blades. For Frontier, using the Bard Peak blade, that's 128 nodes. But if you're using an all CPU design, HPE has designs that have 4 nodes per blade, so that would be a 256 node chassis. But for us, it's 128 nodes, and we use all the power. I don't think I mentioned, but that cabinet is capable of 400 kilowatts, and we use just about all of it. There's 512 NICs inside the cabinet. In the back, there's 32 switches, and that is one Dragonfly group. And this is what they look like. This was during the installation. This was the first few cabinets that showed up, showing the front on the left image. You see those red and blue cables. That's the cold water in and the hot water out. And then those big black things laying down, that's the power cables. There's 4 of those per cabinet. They're about as big as my wrist. On the right image, you see the back of the cabinet, and that is the switch-to-switch cables. That's all that's there. That's all switch-to-switch to implement that Dragonfly all-to-all. So I'm assuming most of you know what a Dragonfly group is, but if you don't, it's a group of endpoints connected to switches, and those switches are connected together in an all-to-all. And then a Dragonfly topology then is a set of groups that are connected all-to-all. So every group has one or more links to every other group. This is similar to how Cray would show it, and now HPE. I prefer to think of it this way. If each one of these blue circles is a switch, it's connected to every other switch in the group. What you don't see is on the edges of those blue dots, there would be hosts connected to it. And I didn't show those just for clarity. And then once you have a group, then the Dragonfly is kind of a recursive all-to-all. So you have all-to-all groups connected together in an all-to-all. And this is what it looks like in practice. So the cable trays are running up above. You see those trays running across the center image at the top. And then the image on the left is all those cables laid out. And it's spaghetti. You don't want to have to replace a cable. You just leave it in place and put a new one in if you need to. There's over 160,000 ports in the system between all of the switches and all of the NICs. And so the fabric manager has to keep track of all of those. And then we talk about the cable counts here. L0 in HPE terminology is the connections between a switch and an endpoint. And so there's a bunch of those. The L1 cables are the switch-to-switch connections inside of a group. So in our case, that's all of those black cables inside of the chassis, or I'm sorry, inside of the cabinet. And then the L2 in their terminology are what they call the global links. So those are the ones that are the teal cables that go up out of the cabinet through those cable trays. And every cabinet has, on Frontier, 2 of those teal cables going to every other cabinet in the system. And there's that cable is actually what they call a bundle. There's actually 2 links running inside of that. So traditionally a single link is a bidirectional, so there's 2 fibers, but this one has 4. So there's actually 2 links in each one. And so each group in Frontier has 4 links to every other group, every other compute group, not counting the storage and management groups. Okay. So initial performance. So there was a lot of concern, not a lot. There was some concern within the lab that hooking the NICs up to the GPUs instead of the CPUs might impose a performance penalty if you're running from the CPU. And this game, they came from the people that were using the machine learning frameworks because they don't tend to do a lot of optimized communication. And what you see here is just using the OSU suite from DK's group. There's no difference whether you're sending from the host or you're sending from the GPU. Latency wise, you see, there's no difference whatsoever. Bandwidth is a little bit different. You see a little bit better memory on the left, GPU memory access here on the left. This is a unidirectional bandwidth. GPU memory is slightly better than the CPU memory. And when you look at bidirectional, you see a much larger difference. And part of this is due to the fact that the CPU here is running in NPS4 mode. And so what they're doing right here is they're hitting the limit of what 2 memory controllers can do. They can only do 25. Now, if they interleave that buffer on the host, so they could use all the memory controllers, they could get it up closer to that blue line for a single NIC, but they can't do that with all 4 in an HPC application. If you're using 4 of those, you can only get about 100 gigabytes a second out of Trento if you're not using non-temporal loads and stores. And so, real applications are going to see better performance out of GPU memory, and that's what we expect in the use is GPU memory, and not have to go back to that host link. Okay, and then mpigraph is something that we at Oak Ridge really came to appreciate during the deployment of Summit. This is a benchmark out of Livermore, and it measures send and receive from all rank pairs. So in the first iteration, everybody is sending to the rank on their right and receiving from the rank on the left. And then the next iteration, they're sending 2 to the right, receiving from 2 from the left. And so when it's done, you've done n-squared communication. Everybody has sent to everybody and received from everybody. There's no incast. And it's really excellent for identifying bad hardware. When we were standing up Summit, we started running this application, and we would see a black line running horizontally and vertically, and it would point to the switch that had a bad port or a bad cable. And we would notify IBM, and they wouldn't believe us because they were using the normal IB diagnostics, and they were saying it's fine. And then we would point it out to them, and then sure enough, when they looked close, they found a problem, and they would then repair that part or replace that part. And what you see, what mpigraph can do is show you if you have differing performance throughout the fabric, it will identify that. And if you look at the mpigraph web page, you'll see some interesting patterns from machines, going back, 10, 15 years ago. So it's a great diagnostic tool. And what you want to see is basically you want to see uniform color, and you want to see uniformly bright color. And that's what you see here. This is an image of one from a single cabinet of Frontier. You maybe see a little bit of blocking here, but it is very, very nice, uniform. The black diagonals, because we did not want to measure on-node communication, so we just basically returned 0 so it wouldn't distort the image. And then this histogram down here in the lower right is something else that mpigraph outputs, and this shows you the tightness of the distribution of the sends or receives, depending on which graph you're looking at. And so for a single cabinet, this is really good. We're trying to figure out how to run this on all of Frontier, but because it's n-squared, we're having an issue with where do we store the data right now, because the file system's not yet mounted. And it takes a long time to run. And so hopefully we'll get some results in the full system here in the next week or two. So where does OLCF go next? Even though we're still bringing up Frontier, we're starting to think about what comes next. We have this long lead time procurement cycle. And so we're trying to talk to vendors to understand what they think. Roadmaps don't go out 5 years, but we're trying to get a sense from them, where do they think technologies are going, and what kind of solution would be available in that timeline. So one of the things we're looking at is, there's a lot of interest in 3D stacking. You see it now with Intel's Ponte Vecchio. They're doing some 3D stacking. You see it now with the Milan X from AMD, where you're putting memory on top of logic. HBM is already 3D stacking, that's memory on memory. And so people say that 3D stacking will extend Moore's law. Density-wise, yes, area-wise, but cost-wise, it definitely doesn't. But if you can do this vertical stacking, one of the promises is that you get much more bandwidth between the components going vertically, because you're not limited by the perimeter of the chips. And if so, how will networking keep up, right? If networking is still done on that perimeter, that perimeter is not going to grow nearly as fast as what's inside the area of the chip, and now the volume of the chip as it goes 3D. And so that's going to be a big challenge for us. If PHYs don't keep up, does that mean we need more endpoints? And if that doesn't keep up, what other options do we have? Will silicon photonics and passive fiber become reality, or will that continue to exist only in the labs? And by labs here, I mean the vendor labs, not the DOE labs. This has been the focus of a lot of DOE investment, as well as other agencies, is my understanding. There was hope that we might see an option for Frontier that might allow us to go down this path. Having a passive fabric, fiber fabric, is really nice because there's nothing to upgrade. You can leave the fiber in place and do basically what we did with the upgrade from Jaguar to Titan, and that is reuse the network and not have to relay all new fiber, which is very time consuming and people consuming to do that. But these are very complicated devices to manufacture, and it turns out in our time frame it just wasn't competitive cost-wise. And will we see new topologies? Or are we just going to see variations of Fat Tree and Dragonfly? With Fat Tree, you can do tapering, you can do a 2-to-1 oversubscribed or a 3-to-2. Dragonfly, you can vary the amount of global bandwidth, but are we going to see anything new in this time frame? Both have their pros and cons. In my view, a non-blocking Fat Tree is the gold standard. The problem is cost. You have all those extra switches because it's an indirect network and all the extra links. And so those ports and those links cost money. But you have the by far the best path diversity. One of the downsides also in addition to cost is floor space. You need additional space just for those large director switches, and floor space for us is always a premium. The designers of Dragonfly targeted the cost of Fat Trees, and they tried to design a system that would allow you to use the less expensive electrical links everywhere you could, which means inside of a group or inside of a cabinet, and just use the fiber or the long reach between cabinets. You can see, that cost savings comes from both a lower link count and less path diversity, it's more difficult to deploy. If you're building a system up, your bandwidth starts out very, very thin and doesn't get to be very good until the last cabinet or two are in place. And so, and likewise, if you're shrinking a system because you're building something else, it's problematic because you lose so much bandwidth so quickly. And then lastly, is there a role for DPUs or IPUs? It depends on the vendor you're talking to, what they call it. These are enhanced NICs with compute capability. Do they have a role in traditional HPC, or are they just better suited for the cloud? Sometimes when you talk to a vendor and they say, you can offload your socket communication and, free up those cores so that you can use all the cores. And you have to point out to them, we've been doing kernel bypass for, a couple decades. And so that's not necessarily useful for us, but they have other capabilities like encryption or compression or some, filtering of data. And the question is there a value for HPC that justifies the additional cost? And that's something that we're very interested in. So with that, I think I have left you a few minutes for questions.
So we have time for questions. Anybody? Yes. Please use the microphone.
Okay. Hi, I'm just about to the so thank you very much for a great talk. And my question is on the file system. So you didn't mention about the connection of the node and the file system. So how do you do it?
I'm not picking up the speaker. If there's a mic, I don't know if it's engaged or if they can move close to the mic, that'd be great.
It's not working.
So I can repeat the question. So the question was about the file system.
Yep.
How is it connected? Yeah. How is it connected?
Oh, how's it connected? Okay, so the file system, well, simply right now it's not connected, but it will be connected probably this week. So the file system is also arranged in Dragonfly groups. There are 5 Dragonfly groups. Each of those, I didn't go into the details, has about 450 servers. And so, I'm sorry, there's 450 servers total. So that's about 85 per, I believe. Those are connected in a Dragonfly group. And so each one of those groups has a bundle or 2 links out to every compute group. And so they, from the fabric point of view, they are just more Dragonfly groups. Does that answer your question?
Yes, thank you. And you mean that you didn't use a file system for the impact benchmark? So.
Well, so we have, you don't need a whole lot to run HPL. So we have a single cabinet file storage block, a Lustre server that's similar to a single unit of the full file system, connected up in the management rack. The issue is they're still standing up the file system. So the file system is just not ready to use yet. They're still doing the bring up of the various components. The goal is to try to bring up the network this week. And so it just was not available. Every lab is a little bit different. For some reason, we like to bring up the file system last, but it creates headaches for the benchmark teams when they get on the system and they just don't have enough space in that little toy unit.
Thank you.
Yep.
Yeah, go ahead, please. Yeah.
Thank you for the talk. Do you understand correctly that you sacrifice one workflows for another or some others in your designing your network? And if yes, how did you choose between these workloads and which are the priority and which are not? Thank you.
All right, can someone relay that question?
So the question was, did you sacrifice the performance of one workload in favor of another workload? If so, how did you make that choice?
So we don't understand yet what the workloads are needing, and we're still trying to figure out what the options are available to us. So in a Slingshot network or any kind of formerly Cray network, you have Dragonfly, let's say, you have the option to do changes to the routing behavior. So you can tell it to use minimal paths only, or you can say you can use all paths. They call that non-minimal, but that's really a misnomer. What it means is don't prefer to use minimal path, but it's a set of all paths which include the minimal paths. And so and then between those choices, you can then say, I'm going to be minimal, but I will pretend that my minimal links are partially loaded so that it will bias it to use some of the non-minimal routes or vice versa. And right now they just don't know what makes sense. And it depends on your application load. It varies if you're running jobs that mostly reside within a cabinet versus if you mostly run jobs that run across a large percentage of the machine, which is what we try to do. If you try to use minimal routing and your communication is really from one rack to the next, you limit yourself to the available links, which is 4 links, versus if you're trying to communicate with everybody at the same time, then the minimal routing is probably sufficient. So it really depends on the application, and we just don't know enough yet to decide how to make that change. There's many other changes, options to tune inside the network like that. So we don't know right now what the trade-offs are, and that's something that we're trying to evaluate.
There was one more question.
Utilizing more from Fujitsu, thanks for the talk. And I have one question about IO network. And I heard your presentation from OLCF about Orion file system. And the presentation says that there are 160 router nodes frontier system that is dedicated to bridge the Dragonfly network and InfiniBand network. So my question is about the router network, and is that router node have GPUs or and the first generation of InfiniBand cards are used in that router node?
So I think what I heard is you've heard that there's 160 gateway nodes or router nodes inside of the Orion file system, and I heard something about InfiniBand cards. So let me say that the compute nodes will access the file system using KFI LND. So that's the native Slingshot interface, basically the lib fabric and the kernel interface to the storage. It is, once you have your job runs, you write to the file system, and then you want to go outside the system to our analysis cluster called Andes, which is just a traditional Dell cluster. you have to get that data out of the system. And so those 160 gateway nodes mount the Dragonfly, they're inside the Dragonfly groups and the storage groups. And then they have InfiniBand cards in them. And that would then connect to our InfiniBand network that goes out to our other clusters, such as Andes. And so the data will flow from the storage servers over HPC Ethernet to the gateway nodes. And then from the gateway nodes, we'll do forwarding, Lustre forwarding, Lustre routing to go then natively over verbs over the InfiniBand network out to that other cluster. Is that what you're asking?
So there are no GPUs in the gateway node.
What was the question?
So there are no GPUs in gateway nodes.
No. The gateway nodes are very simple little servers. I mean, if you think of the traditional 2U box that has the 4 little nodes in it, and those nodes, all they have is a CPU and 1 Slingshot NIC and 1 Mellanox NIC, and that's all they have. There's no GPUs.
So another question about the node count of the frontier system.
Yeah.
There are 9,408 nodes, but the submitted results show that there are nodes, there may be node count that has GPU, maybe 9,248.
Yes.
They're missing 116 nodes. I wonder that there may be the gateway nodes.
No. The gateway nodes live in the file system. It's completely separate racks. Those are standard 24-inch telecom racks. No, that was the 9248 was based on the parameters passed into HPL. They were looking for certain ratios that fit well, and 9408, the full number of nodes, did not fit that ratio well, and so performance would actually be lower. They have run a job at 9408 just to prove that it would run and validate, but the performance is lower. That was just for us. That was just an internal thing we wanted to see happen. But the 9248 was for their ratios of P's and Q's for HPL just made more sense.
Thank you.
Yeah. Oh, I've got to say, being up late apparently is becoming normal for me, because I was up late night multiple nights watching HPL runs, and I was watching the power at the same time. We had live power feed with 5-second updates. It is very impressive to watch a job start and in 5 seconds see the power shoot up about 15 megawatts. It was amazing. I was sure that we were going to get phone calls from the local power providers saying, "What the heck are you guys doing?" Because sometimes a job might crash and then you turn around and you do it again just a few minutes later. And we never got that phone call. And I know somebody that works for TVA, and I called them up and I said, "By the way, we're doing this thing where we're throwing 15 megawatt loads on you. Is it causing any problems?" And he contacted their main office and then called me back later that day. He says, "We don't see it." He said, "We got 24 gigawatts worth of power. A 15 megawatt spike is nothing." So I thought it was impressive, but they didn't think so.
Okay. We have
All
one
right.
more question, Scott. Just hold on.
Okay.
Hi, Rob Turk from Intel. Normally when people stand up things of this size, there's usually some sort of operational gotcha or surprise. Anything you want to share as a parting thought?
Buy me a beer sometime.
What do I get with whiskey?
Yeah. So there were several. The Slingshot Fabric Manager could not scale. We have in a single row, we have 12 cabinets. It couldn't span a row. And then once they got it to span a row, then we tried to do 2 rows and it would fall over. When Cray spec'd out the system, I think we have in the design something like 8 Fabric Manager nodes. But the failover wasn't working yet. So they kept just making the one better. So then it could span 2 rows and they could span 3 rows, and we still have a single Fabric Manager running the whole thing. And they did not think it would scale that large. And that's going to be a challenge for Aurora because the number of cabinets is much higher, which means the number of switch ports and NIC ports is going to be bigger. And that's something that they have to improve as you guys start to deploy up there. So that's definitely one, and that's one that we've highlighted to Argonne to be aware of.
Okay, so with this, let's conclude this talk so that we can remain on schedule. And if you